Okay. So, hi everybody. So welcome to the seminar today. So it's really a pleasure that we have James here. So who is telling us today something about alpha prime corrections and string theory and T-duality. So yes, please go ahead.
Okay, thank you very much for the invitation. As I say, it's really a delight to be able to come here and give a seminar in person. This is my first post-COVID in-person seminar. I think it's a great thing that you've been able to do that because, to me, Zoom is nice, but it's not quite the same as being able to have discussions in the same place. At the same time, I apologize a little bit for being perhaps a little bit rusty at doing these seminars. But anyway, what I'd like to do is to tell you some of my recent, a little bit ongoing work with a senior graduate student, Marina David. She's actually Leo Pandozayas's official student, but we've been collaborating on some T-duality higher derivative stuff. Incidentally, she is going to be on the market for some stuff.
Starting next year.
She's applying right now, basically, for next September. So.
Tell her we have jobs here.
You can tell her herself, so she is virtually taking part in.
I shared the link with her.
Thank you.
So now she knows. Now everyone knows. So I'll be looking at sort of T-duality constraints on alpha prime collections. I want to first start with a quick review of T-duality. It's fairly basic stuff. This is stuff I will be teaching in a few weeks, I think, in my string theory class. But I thought it'd be nice to get off on understanding what the sort of project is. Before I do that, let me just say I've been interested many times in some vague sense, tests of string theory and how can we connect string theory to sort of lower energy effective theories. And if we can't really test string theory, then I think we might have a little bit of difficulty in some sense of justifying what we're doing. Along these lines, I'm not expecting real honest tests. I'm going to go into the lab tomorrow and figure something out, but it's a more hypothetical process. And part of the hypothetical idea is how can I tell the difference between string theory versus like a point particle theory of quantum gravity? After all, when we think about some of the basic features of string theory, there's the string worldsheet. There's also target space or the space-time. We say, well, strings in space-time, at least in a flat background, would have Poincare invariance, Lorentz invariance, probably supersymmetry, or gauge theory, gauge invariance. But those are the same symmetries we have in standard point particle quantum field theories. So there's ought to be something else we can say about string theory, and of course there is. Part of that is the idea of these string symmetries. Of course, we know about T-duality, U-duality, things like that in some sense are inherently stringy phenomena.
But they don't have to necessarily string, right?
Well, in some sense, well, maybe they don't all have to be inherently string, but something like T-duality, I'm going to say, really is not a point particle symmetry, except that if you get to the last point over here, that you do actually see some hints of T-duality from the point particle effective theory. So in fact, we are going to be able to work in in an effective theory approach. But why I say T-duality really is a string symmetry is the sense that it exchanges momentum and winding modes.
String guarantee is T-duality.
Plus,
the string is T-duality. But is it true? Is the reverse true? I mean, if I build up some duality invariant theory, is it obvious that it must come from string? If it did, then what's the meaning of Swampland, right? I mean, Swampland program asks the question: is there any theory which can be UV completed?
UV completed,
and yet not a string theory.
Right. No, at some level, I don't know the answer to that question, but another point of view is how strict are we going to be in the definition of T-duality. And I'll be very fast and loose with it. But in some strict sense, well, I mean, you can already see what I'm saying over here about T-duality. But the point is, I really think of it as a string symmetry. I am actually interchanging momentum in Whiting modes. And the point of having a Whiting mode is more or less a closed, well, there's open string T-duality, but let's focus on closed string. And a closed string wrapped in a circle is not a point particle thing. On the other hand, you're very familiar that you can still look at continuous ODD symmetries or something like that, and the low energy effect crunch. And so if I'm going to demand ODD invariance or something like that, that is also a version of T-duality.
That's what I had in mind.
Exactly. And so when you say something like that, it's not obvious that it must come from string theory, but it feels like it probably does. Yeah, so no, there are questions like that. I agree with that. But if you really focus on the string theory aspect of it, it really is, say, if you compactify one of the space dimensions in a circle, you have the standard Kusa-Klein momentum modes, quantizing 1 over r. You have a string winding m times around the circle. Just look at my string theory class, you can do the mode expansions, you look at the zero mode part over here, and you realize that there's a nice r goes to 1 over r symmetry over here, which sort of flips the first and the second term. It flips the momentum and the Whiting modes. And because P left and P right, there's a minus sign over here. P left is mapped to P left, P right is mapped to minus P right, which is sort of implemented on the worldsheet as X right goes to minus X right. On the other hand, left and rights perhaps are a little bit artificial separation. There's some zero mode stuff that ties it together. So you can also think about it in terms of holomorphic and holomorphic cards, dx versus d bar x, one of them flipping a sign and the other being inert under T-duality. And from this point of view, it's not very obvious from this slide that I wrote over here, but it's familiar that if you think about circle compactification, we do have sort of a U1 gauge symmetry that's enhanced at the self-dual point. At r equals square root alpha prime, r goes to 1 over r, stays at the self-dual point. You have a SE2 times SE2 enhancement. Basically, the e to the ikx modes or e to the ipx modes, the sort of so-called W bosons become masses at that point. You have an SE2 enhanced gauge symmetry. What we can find is an SE2 symmetry operation that actually implements d bar x goes to minus d bar x. So it is actually, can be realized as an exact gauge symmetry, exact symmetry of string theory. And the reason I stress this is because I'm going to claim that we can also look at T-duality for alpha prime corrections. And you might get worried about, well, if I didn't know the structure of the string sort of T-duality map, maybe, the two derivative action is T-duality invariant, higher derivatives. I don't know. But this to me is a hand-waving proof that term by term in the alpha prime expansion, each thing should be ODD invariant by itself. And incidentally, I've already said ODD. The example over here is just one dimension on a circle. T-duality is just a discrete Z2 symmetry on a circle. R goes to 1 over R, but of course, on a d-dimensional torus, it's ODD over the integers, like that.
But in presence of fermions, can you really have ODD? Shouldn't it be SODD?
Probably SODD. There's also issues with fermions. So about 2A, 2B, flipping around and things.
So when you say ODD, it's modular those subtleties, right?
It's modular subtleties. Okay. Absolutely. Okay. This is the 5-minute overview. This is not good. But you're absolutely right about that. Oh, after justifying, T-duality as a symmetry, I'm going to change the pace a little bit and work more or less from now on in space-time in the effective theory. And again, for the bosonic string, no fermions, nothing very fancy, or maybe even some NS sector of some superstring. We have a familiar two derivative effective action. And so Herbert's got the dilaton, it's got the B field over there. And you do conventional torus reduction as you learn in Cosmological theory. And you realize, of course, you reduce the 10-dimensional or upper dimension, graviton into G mu. And then reduced on the circle, you have, in some sense, the Cosmological gauge fields, or perhaps, momentum gauge fields. You also have the winding or the B mu gauge fields over here. You cleverly regroup everything together, and you define a 2D by 2D matrix of scalars over here. I've removed indices. This is internal Gij, this is internal Bij scalar components. This is a very fun combination. It's basically a generalized metric on ODD. And then, of course, you group the momentum and winding gauge fields together. And you find a reduced Lagrangian that looks like the lower dimensional components are the dilaton and the gauge field over here.
Can you remind us where the A and B come from? Just quickly.
What these things are? A mu is the graviton as it comes from gauging the U1 isometries.
Cosmological vectors.
So these are Cosmological vectors. A's are the Cosmological vectors.
These are coming from.
And B's, you have a B mu nu 2 form, right? And you put one leg on a torus. And so it's these guys over here.
Those are the only scalar vectors.
This is why you get
Okay.
two copies. You get D plus D. You get the A's and the B's when you reduce like that. And that's usually what I think about when I think about T-duality interchanging so-called momentum and winding U1 nodes, something like that. Those are just words, of course. But it's interchanging the A's.
Is the inclusion of Young-Mills fields too much of a headache in this or not? I don't know. If you are going to take the theoretic string with Young-Mills set there, then
in those
are
are
you
the best.
forced to take a billion, 16 a billion vectors to do this or not?
Well, I'd say the best or easiest, I should say, thing to do is certainly with the abelian vector. So work at a generic point on the lattice, right? And then ODD gets enhanced to OD 16 plus D or something.
But if I take Young-Mills, what happens? It does not show.
Yes, if you work at some enhanced symmetry points, I'm no expert on that. I don't do that. There are some ideas of so-called non-abelian T-duality. I don't know the whole story with that.
It's supposed to fall. Okay.
Yeah, but at the moment here, there's no higher dimensional gauge fields involved. So everything is what you see is what you get. The Cosmological gauge fields here and the B mu gauge fields over there. And the lower dimensional Lagrangian reaction can be written in a very nice compact form, which I already said is the lower dimensional version of the higher dimensional action. This is scalar kinetic. And then this is the U1 fields, basically. And the way everything is grouped together makes ODD manifest more or less. Because the scalar matrix, or the generalized metric over here, transforms on both sides, omega H, omega transpose, omega is an ODD matrix. And you can see, well, I didn't write down F. F is dA, of course, it's the field strength.
I hope you'll forgive me if I have ask a very quick question. If I truncate the vectors, both A and B.
Wipe them out, make them 0, or what?
0. I set them to 0.
So just get rid of this.
Yeah, digital.
Yeah.
You still have the term in the middle,
I still have this,
which is non-trivially still ODD.
which still has to be transforming properly under ODD.
So we still have ODD invariance. Now, what's the meaning of that model where you don't have any vectors associated with winding modes, etc.? None of that stuff going on.
I would say
is that still a duality symmetry like that?
I would say it's a consistent truncation. It's not supersymmetric, but it is a consistent rotation to get rid of
But
that.
still, you can talk about duality invariance.
Absolutely. And you really beat me to it.
Okay.
For the rest of this talk, I'm going to erase that.
Okay.
And I will look at this one. So, so you already anticipated what I'm trying to do.
Thank you.
Absolutely. But that raises, this point I mentioned it before. I think most of the time when I think of T-duality, I think about the idea of looking at what happens to these A and B fields, to the gauge fields, the momentum winding sort of. Well, no, these are not string momentum modes, winding modes. They're in quotes, momentum winding gauge fields. It's the U1 fields with that sort of interpretation. They're just massless, Maxwell fields. But nevertheless, I usually think about T-duality as acting on the U1 fields over here. And this is not original to our work, to be honest. We noticed, I mentioned it again, some work by Holman's Reebok, plus a few others, that focused on the scalar sector and realized you can get information just from the T-duality or the ODD invariance of the scalar sector alone without worrying about the gauge fields. Incidentally, another minor point, of course, is what you see over here is continuous ODD invariance of the Lagrangian. The T-duality is actually over the integers over here. It's discrete ODD transformations. It's very, very typical in the Lorentz theory or in the effective Lagrangian. You don't see the mod integers or something like that. You just see it as a continuous symmetry over here. So this is more or less a standard. This is a very standard torus reduction, two-derivative action, ODD invariance in lower dimension. The question is what happens when you do the same thing with alpha prime or higher derivative corrections. And I already tried to indicate that because it's a symmetry of string theory, all the alpha prime terms should also be, in a nice sort of ODD sort of fashion. So let's look at, what happens a little bit. There's something to watch out for, of course. If you think about what kind of stringy corrections there are, at least for the perturbative corrections, you usually classify them as alpha prime corrections and string loop corrections. And so what happens is different between sort of tree level and loops. And I'll just make a statement right now that the tree level part, to all orders in alpha prime, order by order in the perturbative expansion, needs to be ODD invariant if it's coming from string theory. And sort of a hand-waving way to see that again is that the string momentum and winding modes, not the gauge fields, but the actual, n over capital R and m times capital R, kind of string momentum winding modes decouple from the massless external fields in the tree level action. And so they don't really care that they're being interchanged or anything like that. And so the Cosmo term, the tree level term is where we're going to look for ODD invariance. Whereas if you think about the string genus or the loop expansion, one loop, two loops, higher loops, there you can actually have string states running through the loop. And in order to see T-duality in the loop part of the effective action, you really have to include sort of the string tower states, the string momentum and winding modes, which we do not do. So typically you say you don't see T-duality in the effective Lagrangian, except for the tree level effective Lagrangian. So I've also been involved in calculating, one loop R to the 4 corrections and things like that, constraining one loop H squared R cubed and so on. Well, I'd like to do that, but I cannot use T-duality for that. For T-duality, it's the tree level terms that we can look at. And so the idea is to sort of demand T-duality invariance into alpha prime expansion and use that to constrain sort of the form of the tree level effective action as much as you can. And you might even hope, can T-duality invariance sort of constrain everything? Is there going to be a unique answer at each order in alpha prime just from T-duality?
What about supersymmetry?
Supersymmetry is also something to do. And you would also hope that, right, you start with R squared or something S for supersymmetric completion. That fully constrains the rest of the terms, as well. At least up to maybe a few small number of possibilities.
T-duality alone cannot tell you that it's supersymmetry, I suppose, right?
Probably cannot tell you no, but there's something interesting, which again, if I jump ahead a little bit.
A conceptual question, is it guaranteed that ODD invariant generalization of the higher derivative corrections to supergravity, is it guaranteed that the ODD invariant higher derivative extensions exist and that it's a matter of working it out? Or is there no guarantee that you can succeed in the
I would
ODD
say
invariant?
T-duality is a little bit tricky in the superstring, as you've already hinted at, that I've sort of glossed over. You know, with fermions, with things like that.
About string theory, you give me a supergravity, and then I do reduction, and I get ODD invariant at 2 derivatives level. Yeah.
Right.
Question: if I want to do merger procedure, I know nothing about string theory. I do merger. Am I guaranteed to succeed in finding 4 derivative invariant in which ODD is preserved?
Let me turn around a little bit and ask, let's pretend you can construct all supersymmetry invariants. Then the question becomes, are those supersymmetry invariants automatically ODD invariant? Or could it be supersymmetric without ODD? Right? Something
So that answers my question. Then that's not guaranteed. Then.
And my feeling is it's not guaranteed. I don't know the answer.
Just having Susie and merger procedure is not enough.
My feeling is Susie is not enough to guarantee ODD.
It's a non-trivial point.
No, this is my feeling, right? My intuition. I'm not making any claim to know anything deeper about that. And part of the statement from that is there's no obvious reason that a field theory needs to have ODD invariants. At least I don't think so.
Even if 2 derivatives one has, that's
right. But you might imagine Susie invariants breaking up into sort of 2 classes or something, right? The ones that are ODD invariants, Susie, and then the ones that are ODD breaking Susie or something like that. But
wow.
But again, the point is, why not? I have no reason to believe one way or another on that. On the other hand, if I'm thinking about string theory, that's both supersymmetric and has T-duality from a worldsheet perspective, then the low energy effective action corresponding to that string theory should have both. Well, assuming Susie's not broken and things like that. So nice torus reduction.
So since there's also Susie in string theory, so you are telling me now that there will be in the after all, because string theory guarantees it.
I think string theory guarantees at least there will be supersymmetric ODD invariants. But that might not be a complete set of invariants. That's the thing.
Okay.
But these are very good questions. There are a lot of questions I don't have to answer. Those are the best kind of questions. So, I guess at the end, I don't have any fantastic sort of answers to questions. I might have more questions. But at least we're going to see, hopefully, some interesting sort of consequences of demanding T-duality. As I said, a lot of my original thought about T-duality was interchanging, gravity photons on BB U1 fields, and demanding sort of nice invariance of the action under those interchanges. But what was kind of fun was to realize that the scalar sector alone also needs to be ODD invariant, and that is a non-trivial sort of constraint on the scalar couplings. And so it's really some work by Olaf Holm and Martin Zwiebach. And then this is a slight, a few years back, just last year, Codina, Holm, and Marquez presented a look at the type 2 alpha prime cube R to the 4 correction, and just looked not even at the scalar sector, only at the metric scalars, Gij, the internal metric components. To them, that was more or less enough to provide a check on T-duality. And that surprised me a little bit, because I thought if I wanted to look at scalars, it should be Gij plus Bij, right? The full generalized metric of the torus. But even just Gij internal metric components enough was able not necessarily to prove ODD invariance, but to provide a necessary condition or a consistency check. Now, of course, what they did was sort of the best way to focus on the scalars was to reduce 10-dimensional string theory on a 9-torus until you have a theory of time only. Everything becomes either a scalar or is gauged away. And so there's even no question about looking at the gauge fields. But of course, they weren't necessarily the first ones to do that. I think Meissner, sometime back, sort of pioneered this idea of a so-called cosmological reduction. Mahdi and Hadi also made some nice sort of statements along these directions as well. And other people have sort of taken over, and I haven't listed all the possible references. Now, our interest, started with this, what I'm going to describe right now, this idea of a cosmological reduction. But of course, you can do T-duality on a single circle. You don't have to reduce all the way down to one time dimension. You can look at T-duality with double field theory, which some of these people like to do. And there's been a whole bunch of explorations that I'm not even listing over here on T-duality and higher derivative corrections. So I'm only telling part of the story, I suppose. As I said, I should focus on saying I already introduced the generalized metric on the torus, this curly H. Eta is the ODD invariant. So it's convenient to write this as a combination, this curly S combination over here, which we're going to use a lot. And that's because the curly S combination transforms as omega S, omega inverse. So if I take a trace of a whole bunch of S's, that's automatically ODD invariance. So once I see a bilinear transformation like that, the best way to make invariance is just to take traces of powers of S. Until you realize that S squared equals 1. And so you really don't get anything very interesting about that. In order to get non-trivial traces, you take derivatives. Traces of derivative of S, d squared S, and so on. And so you can form the whole family or whole set of ODD invariants by taking traces of derivatives of this internal S matrix. For simplicity, and I'll get back to this, but for simplicity, let's say you just take trace of single derivatives of S, d mu1s, d mu2s, d mu3s, and so on. And S itself is a little bit complicated, but if you actually calculate this, at least for an even number of DS's, you find out it's a very interesting form. It's just a trace of a string of what I call n plus n minus, n plus n minus, and so on. And n plus n minus is more or less the derivative of g plus minus b. These are matrices, so this is all a very shorthand notation. But it's an alternating set of terms with g plus b, g minus b, g plus b, g minus b. So left-hand side over here are ODD invariants built out of the scalar matrix S. That's more or less by construction ODD invariant. The right-hand side over here are derivatives of scalars, derivatives of GIJs and BIJs combined in this n plus minus matrix. Incidentally, I could more or less invert this to say the derivative of Gij is sort of n plus plus n minus, or maybe divided by 2 or something like that. I could say Bij is n plus minus n minus. So basically, on the right-hand side, I could think of as combinations of derivatives of the internal Gij and the internal Bij. So if I did a Kaluza-Klein reduction on the torus, I don't automatically see S. I see the right-hand side. More than that, I can see the right-hand side without alternating plus minus plus minuses. I could see n plus to the 4th power or something. Who knows? Why not? So this is the point that not every reduction on a torus, not every term in 10 dimensions will reduce to an ODD invariant in lower dimensions, in 1 dimension, or in whatever lower dimensions you work at. But of course, you already knew that. There's a bit of a hint, well, which I'll come back to, that this G plus B or G minus B is a very natural combination that you see from a string worldsheet point of view. After all, in the NS sector, you think about the closed string as sort of a tensor of left and right modes, and the generic polarization tensor is sort of G plus B, something like that. And it's not entirely G plus B, but this is also sort of the background for why you might have a generalized geometry picture, which can be sort of made a little bit more manifest when you have an actual torus. So I did this sort of in generic dimensions. So d mu's are lower dimensional bridges. But you can get a big simplification by reducing all the way to time only. So reduce all the space dimensions. That means the only derivatives you can do are time derivatives, which I would call dots. So some people call this the cosmological reduction because you reduce everything to just functions of time or something like that. And then instead of d mu1s, d mu2s, d mu3s, so basically everything, every derivative, every time derivative is just s dot. And so the ODD invariants or O99 invariants are just traces of powers of s dot. It's not obvious. I didn't even write it down. An odd number of s dots vanish. But of course, we're not even going to make invariants with odd number of derivatives. We have 4 derivatives, 6 derivatives, 8 derivatives, invariants like that. So it's okay to restrict to even powers of s dot. And if you rewrite that in terms of gij dots and bij dots, you get this alternating strings of n plus n minus n plus n minus and so on. So normalization factor in front. And so this provides sort of a roadmap for exploring T-duality. This is something that Holman's, Reebok, and a few others have pioneered. The idea is, let's say we have a 10-dimensional action and we want to construct 10-dimensional couplings that are T-duality invariant. But we don't really know the answer at first. Let's just write down a parameterized set of couplings. So let's write down all possible gauge invariant 4-derivative couplings, all possible gauge invariant 8-derivative couplings, things like that. Perform the reduction to 1 dimension, and what we'll find is sort of a 1-dimensional effective action, other than the 2-derivative term, which I did write down, tree level. And this is following Holman's, Reebok's notation. They've defined the 1-dimensional dilettante with a factor 2 removed for some reason. But the point is, 1-dimensional effective Lagrangian would be written in terms of G dot, B dot, and phi dot. Dilettante, an internal metric, and internal V field. And we take, just some nice combination called capital L and capital M. As I said, if you just take some 10-dimensional term, reduce it to 1 dimension, you just get some functions of L's and M's, you're allowed to rewrite that as a function of m plus and n minus. And these are, in some sense, Lorentz invariants. They're scalars in the 1-dimensional sense. So they are going to be traces. You're not going to have open, internal indices. However, the traces may not be n plus n minus n plus n minus alternating. You got traces of n plus n plus n plus n minus and things like that. So it becomes not trivial. Not everything is T-duality, right? But the point is, now you impose ODD. And what I mean by imposing ODD is to make sure only traces of alternating pluses and minuses are remaining.
But you can't impose that, right? You get what you get from the reduction. I don't understand.
No. Sorry. You get what you get from the reduction, except that what I'm proposing here is you use a parameterized set. You put in unknown parameters in 10 dimensions. There's 2 ways to look at that. One way is if you know what the 10-dimensional couplings are, what you see is what you get. Yeah. You do the reduction, and then you ask the question, ODD or not? Is it invariant or is it not? And that's been done. And I'll do that for the further.
What else can you do?
The other thing you can do, which is what motivated us, is suppose you don't know the full set of couplings in 10 dimensions. Let's say you don't know the completion of R to the 4 in 10 dimensions.
I see. Okay.
So you can write R to the 4 plus a whole bunch of parametrized couplings with constants C1, C2, C3 up to C800 or something like that. Do this reduction procedure, you get a whole bunch of terms in one dimension. Make sure all the non-invariant terms have 0 coefficient. It's a linear algebra problem because everything here is very linear. And then you demand, all these linear relations on those 10-dimensional couplings. And if you're lucky, you have enough relations to completely fix things. So even without doing a string, 8-point function or something like that, you might be able to actually find the original.
Symmetry. Suppose you are.
Or supersymmetry. Yeah.
Yeah. Suppose it's too hard to do 8 derivatives through the 10 dimension. You don't want to do that. You're saying just write down parameterize and do this.
And do this.
Okay. Fair enough.
Well, turns out going to time, it's not prescriptive enough. I'll tell you the answer right now.
But again, SUSY will not be guaranteed.
SUSY is not guaranteed at all. Yeah. And whether it really is a string theory is not even guaranteed.
So
until you impose enough sort of.
You are guaranteed that you have a solution to the algorithm.
You're not guaranteed to have a solution, but it seems like you always do. And the reason I say that is it seems like there's enough freedom in parameterized terms. You start with all possible, Lorentz invariant terms up to some field redefinitions or something. There's a whole bunch of them, 800 of them or something like that. So it feels like there are enough parameters. So all the cases I've seen, there are more than enough degrees of freedom in 10 dimensions to find a solution.
Do you avoid higher than first order derivative?
Good question. Absolutely. So I cheated on this slide because I only look at first order derivatives, right? Yeah. If you think about Riemann as two derivatives, at least the linearized part of Riemann is two derivatives on the metric fluctuation. It would be Gij double dot. So it would be two derivatives on Gij. It would be L dot or N dot or something like that. So you go to this page. And as I said, as you pointed out, you do have things. If you're building things like out of Riemanns or things like that, if you build things out of derivatives and Riemanns, you might even have more than two derivatives. The same procedure works, and this is where the reduction to one dimension can be very powerful. Reduction to one dimension, in some sense, simplifies things almost too much, so you lose information, but it also allows you to do manipulations that you don't quite get to do in higher dimensions. And one of the things you can do is to write down sort of one-dimensional two-derivative equations of motion. One of the worst things about working with higher derivative effective actions is the idea of field redefinitions. There's so much freedom in field redefinition, all these different possible field redefinition frames. You're never quite sure if things are equivalent or not equivalent, up to field redefinitions. But you can use that to your advantage also. And here I'm thinking about functional field redefinitions, which means I'm going to, in quotes, add 0 by adding two derivative equation of motion terms. And in particular, I'm not writing out the equations of motion, but I'm going to give you two of them. One of the equations of motions is, this is more or less a scalar equation of motion. Box phi equals, or box Gij equals to 0 is n dot over here. And already is a derivative on Gij and Bij. So n dot is two derivatives. So this is the box of Gij plus Bij, so to speak. And the right-hand side is what you get. And the right-hand side is first derivatives. So you reduce two derivatives into a product of first derivatives by using the scalar equation of motion. The dilettante equation of motion, phi double dot, reduces to phi dot squared. There's still a typo here, just phi dot squared. So this allows you to reduce two derivatives into one derivative. You can repeat this. I can take a dot at both sides. I can reduce three derivatives down to two derivatives down to. wondered if, in some sense, I can always reduce things to a single vertex by using equations of motion. This is not something that can, in general, be done in higher dimensions. But in one dimension,
Have you done that by using equations of motions that are already not lowest order equations of motion, which are the first order?
Some groups, I think, have looked at that.
Have you done that far?
I have not.
Okay.
So what we have done is to take the second order equation plus one perturbation. So Einstein-Hilbert plus alpha prime, or Einstein-Hilbert plus alpha prime.
Then it's enough to use the lowest order field equation.
Precisely, exactly. So we've only used the lowest order.
Okay. Okay.
But some people, alpha prime q plus higher is really bad. But you can go Einstein-Hilbert plus alpha prime, and then go to the alpha prime squared, for example, the next order there. And to keep that sort of consistent, then you're going to have to go to one higher order in the equations of motion. And that has, to some extent, been looked at recently. So the important thing here was to reduce everything down to single derivatives. There's another bit of a subtlety, which is not super important, but I just mentioned it anyway. Phi dot squared, and this is phi dot squared. Phi dot squared, dilaton phi dots. This is the lower dimensional dilaton. The lower dimensional dilaton is already shifted by the volume of the torus. The lowest dimensional dilaton is inert under ODD. So something like ODD squared on the left-hand side. Sorry, phi dot squared on the left-hand side is ODD invariant. The right-hand side, this is up to some factor of -2. This is basically trace of S dot squared. This is also ODD invariant. And you can use equations of motion, field redefinitions, to shift between left and right-hand sides. So you might want to eliminate the redundancy. And one way to do that is to go into, in some sense, a canonical basis of ODD invariant terms, which are written entirely without the dilaton. So you can find a canonical basis of n plus n minus only, and no dilatons. And the way to do that was explained by Holman's Riebeck by using appropriate combinations of equations of motion and integration by parts and effective action. So integration by parts just means you are throwing away total derivative terms. You can reduce the power of phi dots. Phi dot to the k goes to phi dot to the k minus 1.
Is this special to cosmological reduction case only, or?
This is special to cosmological reduction. This is specialized to one dimension.
It may not work.
No, yeah. This is sort of trouble. Absolutely. So you do that, and all you end up with are traces of n pluses and n minuses. That's where you can check, are they alternating or not? And either you know the starting point, you check your answer to make sure they're alternating, or you use an unknown parameterized starting point, you set all the non-alternating terms equal to 0, that provides your terms on the original action. So we'll see how this works. But let me just also get back to this point of what's sort of nice about G plus B or something like that. Gij plus minus Bij. What's nice is you really go back to the string worldsheet a little bit, and you think about scattering of closed string states, NS states or bosonic closed string states. You have the ring 2 massless ring 2 vertex operator over here, which is more or less a left moving part and the right moving part over here. This is written down for a bosonic string, but there are similar features in the superstring. And the rank 2 polarization has a symmetric part, the antisymmetric part, and a trace part over here. So if you're scattering the NS state, you just write down one sort of string scattering amplitude that encompasses gravitons, B minus, and dilatons in one package. There's no need to calculate everything completely separately because it packages itself together in this format. Along the same lines, if I'm scattering gravitons, this is an S matrix amplitude. The S matrix is some function of polarizations and momenta or something like that. What I want to do is to write down an effective field theory that generates the same S matrix. That's what I mean by writing down my low energy effective action. I mean, there's other approaches, but the one I'm thinking about here is to write down an effective Lagrangian that should be gauge invariant, generally covariant and things like that. Which means when I'm scattering gravitons, I'm not going to write down bare h me's in my Lagrangian. I want that to be gauge invariant, so they're going to be Riemanns. So each h over here has to combine with momentum factors to become more or less components of the Riemann tensor. That's what you want to see happen over here. So I'm going to have a general rank 2 polarization theta mn with 2 momentum factors on it. And that turns into a sort of a generalized Riemann, which is an ordinary Riemann over here plus 2 derivatives in B plus 2 derivatives delta, which basically means I'm going to end up with a Riemann or a curvature computed out of a connection with torsion, which is the ordinary spin connection plus the H field, basically. And I'm writing this in the string frame notation. If I did this in a more natural Einstein frame, I'll also have nominal and nominal phi, so 2 derivatives on the delta, which I'm hiding in the string frame over here. This, of course, was known a long time ago. I think Gross and Witten, Gross and Slow all have this type of linearized Riemann with in the Einstein frame, with the dilaton, and with the torsion of the H field as well. So from string scattering at the lowest order, 4-point functions or something like that, what you see is what you get. There's nothing wrong with this, using this sort of linearized Riemann with torsion. Now that means that the linearized at the lowest order, the alpha prime expansion has to look something like this. And I'm not saying supersymmetry. Supersymmetry might remove some of these terms. I'm not even telling you what the kinematical factors are. There's lots of ways to combine indices on Riemanns and things like that. But what I mean here really are Riemanns, not Ricci's. Because more or less, in some sense, the linearized Einstein equation is R mu equals 0. And so you don't see Ricci's. You see combinations of linearized Riemanns with torsion over here. But having said that, part of the question is this is correct for the starting point. But can we actually replace these with nonlinear, the full curvature of a torsionful connection? Can we add any Ricci terms if needed and things like that? How do we go beyond the linearized level, basically, and find the full derivative invariant? So let's look at the cosmological reduction in just a little bit more detail. So basic building block, this is now assuming you're going to construct things out of the full nonlinear Riemann with torsion. For the cosmological reduction, either you're on the torus, IJKL indices, or you're on time, the T index over here. And it's easy to it's not too hard to work out what it looks like. R with 4 legs in the torus, or time I time J, basically. And the linearized Riemann, well, what I mean by linear and nonlinear is this is one Riemann, there's 2 ends over here, there's 2 GIJ dots, so to speak. The linear term is this here, G double dot, or N dot term. This is the linearized term, all the N squareds are the nonlinear sort of parts. The interesting thing is if you actually believe the nonlinear Riemann with torsion is the, in some sense, correct object, the correct geometric object to use, you'll see this N pluses and N minus, N plus things like that. These are 4 open indices, so it's not N plus squared or something like that. If these IJKL indices are contracted in the right way, N plus transpose equals N minus. I'm allowed to write everything in terms of N plus and N plus transpose. Transpose is just contracting or interchanging like the J and L indices or something like that. So if I took R IJKL, if I took the first line over here and did a contraction, and it's important which order I did it, IJKL, IJKL. The Riemann with torsion doesn't have the property where you just move the 2 indices. Right, it changes omega plus into omega minus. So if you contract it in the way indicated, and then you start getting transposes here in such a way that you end up with more or less N plus N minus in alternating combinations. So Riemann squared constructed out of R IJKL is ODD invariant. Riemann, what I mean by Riemann is R plus, R mega plus squared out of R IJKL is ODD invariant. And you say, well, that's really wonderful. That's great. That's what we're looking for. Until you realize the 10-dimensional Riemann is not just R IJKL. You have to have the second term. If you want it to be covariant to 10 dimensions, you're going to have the second term there. And once I contract the second term over here, so a 10-dimensional Riemann squared includes the top line squared plus the bottom line squared. And bottom line squared is not completely obvious, but when it's worked out over here, it's not ODD invariant by itself. So there's a quick and dirty sort of result, which is to take the top line squared, ODD invariant, but not covariant in 10 dimensions. There's another thing you can do, which is to do both of this, the full Riemann. It's covariant in 10 dimensions, but it's not ODD invariant. Now we do want covariance. So the answer is you're going to have to take the whole thing squared. Then we're going to have to add additional correction terms to fix up the T-duality properties of that. So if you had something like 4 derivative Riemann squared, it's telling you you have to add something like Riemann H squared, H, you have to add some other terms to recover ODD invariance.
Okay, RH squared is order alpha prime.
No, everything on the slide is order alpha. Well, not everything, but starting here is this is alpha prime. This
now you're talking about adding alpha prime cube. I don't understand.
Where am I? Sorry. Oh, no. The last bullet point is sort of saying.
Especially when considering the different.
I'm mixing up orders. All I mean is if I start with R squared, I'm going to have to add additional 4 derivative terms.
Okay. And
there's not too many of those. That's manageable.
Okay.
If I start with R to the 4, I'm going to have to add additional 8 derivative terms. And there's like more than 800 of those. And it becomes, in some sense, a little bit unmanageable. So the statement over here is not meant to be the consequence of the previous statements. It's a separate line that says, if I try to fix up R to the 4, it becomes a disaster.
Are there terms involving Ricci, powers of Ricci, Ricci scalar, or is it always involved H and the dilaton? The extra terms that you need. They always.
You might need Ricci scalars or Ricci tensors. It's not.
So you're not claiming that always the corrections are of the type in which you have.
Oh, I didn't put the indices on here. Sorry, this is very abstract. I didn't write out the canonical structure. So this R just means any kind of Riemanns or Riccis. And in a lot of cases, you don't need Riccis. But I'll get back to Ricci. I will definitely get back to Ricci because that's something that really has been bothering us. So we'll start without Riccis. Well, maybe I'll say something about Riccis over here. So if we look for ODD invariance, the question is how do I build ODD invariance which has, H and D phi's and things like that. And so we could try to construct certain building blocks. I copied over the Riemann reduction over here. I changed it a little bit. This used to be 2n dot. I used the equation of motion to write that as 2 phi dot n. There's a real subtlety there. By using the equation of motion, which if I flip back over here, there's an m over here, which is bij dot. This is not m plus, it's not n minus, it's m. And the interesting thing is you take n minus and you add m to it, you get n plus. So what happens is you use the equation of motion to put this into a phi dot n form, but it changes n minus n plus into n plus n plus. And it's in red because n plus is not alternating. This is automatically going to break ODD invariance. End of story. You don't have to say anymore. This breaks ODD invariance. The H field is Bij only, which can be written in terms of n plus minus n minus. So I wrote it like that. The reason I put it in red to say it breaks ODD invariance is because it has a mixed sort of property. Every n plus here goes with n minus, and n plus and n minus put together is not a good object. And also the dilaton reduction The 10-dimensional dilettante is the one-dimensional dilettante shifted by a volume. And so the derivative of the volume term over here gives you trace of Gij dot, basically. This is Gij dot, but the reason I wrote it in terms of m plus is because I wanted to write everything in terms of m plus and m minus. Trace of m equals here. So trace of m plus is equal to trace of m minus. Doesn't matter. I just chose to write it as trace of m plus. I could have written as trace of n minus. No matter what I do, this by itself, end of the story. That breaks ODD. So what you see, the reason I did that trick is to get rid of second vertex. Everything on the right-hand side is now single vertex. And in some sense, the Riemanns are at nonlinear order. One Riemann has turned into two fields over here. And so you can see, the stuff that breaks ODD invariance in the Riemann terms needs to combine with the stuff that breaks ODD invariance in the H and phi terms to sort of restore T-duality. And so most of the nicest results come at the forward derivative level, alpha prime r squared. So let me summarize alpha prime r squared. And this is just actually working out 10-dimensional torsion for Riemann r plus squared. And just plugging in the formulas, I'm not going through the formula details. It's not super important. It's just pushing through some algebra and doing some, as I said, the trick to remove the phi dots using total derivatives. So basically integration by parts, integration of motion brings you down to this second line over here. This is the alternating m plus n minus n plus minus. This is ODD here. It's accompanied by two terms that break ODD. So that tells you, if I just wrote down a string effective action that's alpha prime r plus squared, that's not ODD. Now, of course, when you look at the bosonic string or the heteronic string, there are additional terms. For the heteronic string, this is sort of Birchhoff the root. There is the r plus squared over here, and there's h squared over here. This looks kind of like there's nothing else until you realize that h hat over here has a non-trivial Bianchi. And I can implement that in some vague sense by saying h is dv plus the Lorentz Chern-Simons term, which is constructed out of alpha prime higher derivative sort of stuff. So there's this forward derivative stuff here. There's also a forward derivative terms like here. There's dot dot dot. This is all very sort of cumbersome where h is shown. And you know the answer that this gets expanded like crazy. But anyway, for the forward derivative level, that's all we'll focus on.
Before you appeal on omega plus business, those red curves, are you sure you cannot remove some of them or all of them by Q2 definition?
I'm pretty sure you cannot. And that's because, in some sense, this is the minimal sort of basis. I've already removed the dilettante. And the question is, what other field redefinitions can it do to remove some combinations of n pluses and n minuses? At least the equations of motion have been basically exhausted without putting the dilettante back in. There's some subtlety with quadratic terms, n plus squared, n plus n minus, things like that. So you have to pick a sort of canonical way of removing the quadratic terms. And then you're left with, So I mean, you have trace n squared, basically. Those can be manipulated a little bit. But once you're left with these type of terms, it's very minimal. So heteronic string fixes up Riemann squared by introducing a Lorentz Chern-Simons term. The bosonic string, I guess, let's say if in cyclin, fixes up Riemann squared by adding RH squared and H before, something like that. So for the heteronic case, I already mentioned, you add a Lorentz Chern-Simons term. If you only focus on the alpha prime forward derivative term, then there's a cross term between H and the Lorentz Chern-Simons. There's also Lorentz Chern-Simons squared, which is a alpha prime squared type term. And then it's also built, out of omega, which is H, which has H hat, which is H, and so on. Forward derivative only, this is all you need over here. And student Marina is very good. She did this calculation. I didn't do that. And you end up with something like that. N plus cubed, n plus squared, n minus squared. Flip to the previous slide. N plus cubed, n minus, n plus squared, n minus squared. Check the factors over here. There's a 1/3 over here that cancels the 3's in the numerators. The red terms from this mixed term precisely cancel the red terms from the Riemann squared, giving you only the n plus n minus alternating term. Very beautiful, which is the ODD invariant S dot to the 4. So kind of interesting. If I just took Riemann r plus squared, and I just took the ODD invariant term and just crossed these out by hand, I got the correct answer. The additional term, the additional Lorentz term, Simon's term, in some sense, its job is to remove the red ink, to get rid of those non-invariant terms. The R to the 4 story is more complicated, but in the R squared story, it's very nice. The same thing basically happens in the bosonic string case. This is the original Riemann squared term, RH squared. I didn't define H to the 4. It's not very interesting. There's a certain way the indices go. You compute those things over here. It looks like each of these terms has an invariant term and non-invariant terms. If I actually take the combination, if I take these two terms as my combined correction term, the invariant stuff actually cancels out. There's a factor of 1/3 here. Get rid of the 3 over here. Which means the correction terms taken as the combination also is red only, ODD breaking only. And again, it precisely cancels the ODD breaking stuff in R plus squared. And that also leaves a one-dimensional variant alternating plus minus or S dot. So it's kind of elegant. You get this sensation or feeling that what you do over here is you write down, first of all, you promote Riemann to a torsion for Riemann, which is the right thing to do at the linearized order. You calculate, in some sense, the reduction of R plus squared or R plus whatever combinations. You look for the ODD invariant term, and that's your answer in one dimension. You just throw out all the red stuff. All the other stuff is designed to get rid of the red. However, that doesn't quite work for the R to the 4 terms. I don't know, whether it's supposed to work or it's not supposed to work. We haven't quite seen such an elegant way of the reduction of just, reduce R to the 4, keep the ODD invariant part. That doesn't seem to be the right answer. You need to actually have, the full combinations. So I don't want to talk for too long. So let me just summarize some of the highlights of this. Also because, to be completely honest, R to the 4 is kind of a mess, and we don't have perfect answers at R to the 4. We have more questions than we have answers. But what we do know about type 2, 32 real supercharges is the corrections start at R to the 4 order. In fact, Chris Pope has worked on the sigma model beta function a long time ago and gotten these to 4 corrections. It can also be done by string 4-point functions and things like that. And roughly at the 4-point function level, there's this invariant T8 tensor. At tree level, it's got this famous -3 over here, T8, linearized R to the 4. We're pretty sure epsilon is there as well. You don't quite see that at the linearized level, but if you do 5-point functions, you will find evidence for the epsilon R to the 4 term. If you actually work at the 5-point function level, you will find that replacing linearized R bar to the 4 with the nonlinear R to the 4 is insufficient. This is sort of a brute force string amplitude calculation. You realize that T8 minus epsilon R to the 4 has to be combined with H squared R cubed type terms. This is also some version of H squared R cubed with Lorentz indices in different places.
Are you saying that string amplitudes are not strong enough to give us this result?
No, this is string amplitude. If you calculate the string amplitude, you get the right answer. There's a question of
nonlinear answer.
Yeah, if you calculate, I call it nonlinear. It's a 5-point function. To me, the lowest one is what I call linear. R to the four particle scattering is what I call the linear term. 5-point functions, this vanishes for 4-point functions. The problem with this is it goes all the way up to h to the 8, for example, or d5 to the 8. But you don't get the probe with the string scattering amplitude until you get to 8-point functions. And no one in their right mind, well, maybe someone will calculate 8-point functions. I wish someone would do that. Now, I should qualify it a little bit, because it's okay in some cases to actually calculate these higher point scattering amplitudes. There's been lots of progress in field theory and in string theory scattering amplitudes. The problem is, for me, the scattering amplitude is not good enough. It's not good enough. The scattering amplitude is just a huge function of momentums and polarizations. The scattering amplitude is not an effect of Lagrange. I want to see
Why
the
not? Other than it's being complicated, what's the problem? It's just messy. But
no, it's not just messy. It's also just an on-shell result as a function of momentum and polarization. I don't see Riemanns, I don't see H's, I just see polarization tensors and momentum, right? The scattering amplitude.
But you gave us prescription how to write in terms of Riemann, etc.
Oh yeah, absolutely. So the point is, you want to recreate, you want to write down the effect of Lagrangian that gives you the same S matrix.
Okay.
Absolutely. And in principle, it's turn the cranks, right? But I'm saying that's not an easy thing to do. So I'm saying, if I look in the literature, I can probably find an 8-point function. But I don't have the courage to write down the effect of Lagrangian that gives you the same S matrix as the 8-point function.
Okay, so it's not easy. You're not saying.
No, it's not conceptual problems. It's not conceptual problem. It's just technically very hard.
And you're suggesting your approach, T-duality approach, is the way to go.
Exactly. T-duality might be a way to bypass those type of difficulties. In principle, supersymmetry. You also say supersymmetry completion should also give you other stuff. But that's also a little tricky.
Very messy.
It is very messy. Yeah. Well, let me tell you part of the difficulty over here. As I said, everyone does 4-point functions in a string theory class. If you extend and push a little bit, you can do a 5-point function. This is an open string 5-point function. It's not too bad. It's not the best, but it's not completely bad either. Use the KLT relations, open string, closed string. Now you have an NSNS 5-point function. This has been extended past the 5-point function. But of course, the scattering amplitude also factorizes on the 4-point function and things like that. The 8-point, you're looking for effective Lagrangian, a local effective Lagrangian. You're looking for contact terms. Whereas a 5-point function also has a zeta of 3 4-point function and a standard supergravity 3-point function connected by an intermediate propagator. You have to remove all those terms. So removing all the poles and everything like that is not very fun. Good thing is Richards and a couple of papers already did that for one loop 5-point function. It's not the worst, but it's still a little bit messy. If you look at those papers, it's still a little bit messy. The beautiful thing, and this was a cheat, this is, maybe I should call it a cheat. There's a trick that I worked on with Ruben Benassia. If you subtract the S matrix, subtract the S matrix and amplitude between the tree and the loops, all those intermediate propagator terms cancel out. Why is that? Because in the 2B theory, we know something from S-duality. We know that the tree and the loop are to the 4 corrections, at least in the purely gravitational sector, combined with one of these non-holomorphic Eisensteins. What that means is the kinematical structure is T8, T8 minus 1/4 epsilon 8, epsilon 8. It's the same at tree, same at loop. This is the 4-point function. All this factorization on intermediate poles is because you have a 4-point function on one side and a supergravity 3-point function. Those 4-point functions are the same up to some constants that can be dealt with. So you take the subtraction, and this delta out, the difference between tree and loop amplitudes is a contact term only. And now it's easier to just recreate an effective Lagrangian, reproducing those contact term S matrix elements. And so you take Richard's answer, you add the 5-point terms to h² cubes that are calculated from delta m, and you put it all together. And that's how you end up with this result over here. Not the main focus of my talk, so I didn't say too much about that. It turns out there's additional nice properties that we discovered later on. But anyway, we don't have complete 8-point function. So the idea was to use T-duality to see how much information you can get on these nonlinear completions of arts before. However, I should mention, and this came as a slight surprise to us, Mohammed Gharousi, in some papers last year, actually used T-duality on a single circle. He used T-duality to come up with a complete nonlinear 8-derivative invariant, unique up to an overall constant. Now, what I mean by unique, of course, is unique up to field redefinitions. So in the first paper, he writes out a basis of 864 terms. I forgot the precise number. It's a minimal but complete basis of 8 derivative gauge invariant couplings and dimensions. In the middle paper over here, he uses T-duality to constrain all the coefficients. So a huge, linear algebra problem. And then the original basis over here includes dilitons. And then he realized that by doing field redefinitions, you can remove dileton couplings. So the last paper is basically a remodel of H's and novel H's and things like that. And if you look at the paper, it's a real tour de force. It's Mathematica exact or something like that to be able to do this. So this is no longer 800 terms. I forgot how many terms. It's an order of 400 or something like that. It is T-duality invariant. That's the really fun thing about it.
Just reduction in a circle.
By a single reduction in a circle, you don't look at the scalar sector. You look at G mu naught, D mu naught. You look at the U1 fields.
Only U1 field.
U1 fields is basically all you have, I think. I mean, you have a volume modulus, but a volume modulus, I think, is not too interesting or something. Well, okay, I don't remember the details. But the point is the single circle reduction and T-duality invariance was good enough. Very remarkable. However, and you might say, what's the final answer? Now we know everything we need to know about average. Except there's no structure. So the third question is there a higher level sort of geometric picture? Is it supersymmetric even? I mean, it has to be supersymmetric, if you believe in it. But it's not obvious, just look at the answer. And also, how does it fit, this T8, epsilon 8 expansion or something like that? It's this whole point of field redefinition allows you to shift things around in so many different ways, you're never quite sure if things are supposed to agree or not agree anymore. I mean, yeah, they're supposed to, of course. It's not obvious when you look at some of these long expressions. I already mentioned Codina, Holman, Marquez took the purely gravitational part, so no H fields, no BIJs, but from GIJ dot alone, deduced that the cosmological reduction to one dimension. Let's look at this. L is G dots. And the reason this is a non-trivial test is because there's one more term you could have over here, which is trace of L cubed times trace of L to the 5. Trace of L cubed cannot be completed into an even number of n plus n minuses. It's an odd number of scalar matrices. And a trace of an odd number of scalar matrices, as we have hopefully seen, cannot be T-duality here. And so this is actually a non-trivial test. And then, well, Gharousi had the full set of 8 derivative couplings. So of course, it's very natural for him to plug it in. And this is what he gets. Not just else. This is the whole deal in some sense. Well, he demanded T-duality invariance on the circle. He finds out in the scalar sector, it's also T-duality invariance on the 9 torus. You kind of expect it's supposed to happen, but it's really nice to see that comes out right there. But I still feel like something's missing. What's missing in some sense is, what Dorsey has looked at. What other people will say, of course, is if you look at the Riemann terms, the invariant terms, Riemann terms are not pushed around by field redefinitions. There's just a combination of two Riemanns like that. You take this, what you see is what you get, no more than what's written over here, no dot, dot, dots. This is all you need. This is all Dorsey needs. It's Riemann terms plus H's and things like that. However, there's also good reasons, good geometric reasons, that the arc to the 4 terms should look like this. If you expand the T18, epsilon 8, epsilon 8, you will find the Riemann stuff. You also find a whole string of Ricci's. And every time you have a Ricci's, well, I don't need to go back, but the point is the Ricci's are not ODD invariant. And the Ricci's give you single traces. And the only other places you have single traces are dilettantes. So the point, maybe it's not too obvious, but the end result is when you have Ricci's, you need to have dilettantes. So this is telling you that if I write epsilon 8 arc to the 4, I'm going to have to add dilettante type correction, which we never thought we needed. But our understanding now is that you need to have dilettante photons as well in the spaces. So I think what we're really trying to do, we don't have a quick answer, is to find a T-duality completion of this object over here, as opposed to this object, which is kind of nice, but it's not, doesn't have the structure. This is also more obvious from supersymmetry. So we're trying to tie everything together. And because of time, let me skip some of these things over here, but just to say that it's a lot of open questions. And part of why we're trying to understand this is not just constructing the derivative thing, but to understand what kind of structures, what do you do to go beyond the linearized R plus? It feels like, from a generalized geometry point of view, there's got to be a generalized, curvature of a generalized connection. And it feels like it should be the right thing to use. And yet, the nonlinear R plus is not good enough. Maybe it's R plus plus H squared, or some other combinations. Probably more complicated than just saying it's this, of course. But some of our thoughts are, what are the, more obvious geometrical sort of T-dual building blocks to use? Not invariants, just covariants or something like that. And let me just make a final comment on supersymmetry. T-duality constrains the higher derivative couplings. Supersymmetry constrains them as well. You can vaguely just wave your hand to say, I start with the gravitational sector, R to the 4. And I move around in superspace, I get everything. Problem is, supersymmetry with 32 real supercharges, people here really know well, they think. It's not an easy thing to work on. You can do linearized superfields, but then here we go again. At the linearized order, everything works pretty nicely. It's the nonlinear completions of these terms that are, a real mess. So let me just end with some thoughts of, we are making a lot of progress. We're understanding how to go beyond some of this linearized superfield stuff and how to do some of this T-duality stuff, figuring out some of these nonlinear terms. Good progress in understanding these 8 derivative corrections in type 2 strings. Of course, there's still many questions that remain to be done. Thank you.
Thank you very much for this very nice talk. Are there any questions? We already had a lot of questions, right?
So can you remind us why? For example, if I take a typical, let's say, hydraulic string theory in dimension, we also have S-duality with the T-duality. So, but why don't you look at the other dualities?
Oh, like U-duality or something like that. I think in principle, that's also a good thing to do. This was just, one thing at a time. The best thing to do is to, look at S-duality and T-duality maybe at the same time, right, or something like that. I have to say, this is a very quick sentence over here. There's a lot you can do with S-duality and 2B. Forget about T-duality. Just the 10-dimensional 2B effective action. I already mentioned, there's these non-holomorphic Eisensteins and things like that. There's U1 preserving, U1 breaking combinations. We know certain things about maximal U1R violation terms. So we do know some terms using, we know a lot of things. And this is Michael Green's story. We do know a lot of things using sort of S-duality. But I haven't seen any sort of complete S-duality, T-duality, and supersymmetry all at the same time. Sort of. S-duality, supersymmetry, yeah, that's also been discussed.
I have another question. So how does the whole picture change when you have open string?
Oh, sounds like deep rings or something.
Oh, I thought you alluded to that earlier at the beginning of the talk. That
Oh yeah, this was looking at the gravitational sector. So this is T-duality invariance of these gravitational sector couplings, which are sort of closed strings. And so even in a theory with open strings, there's still a closed string, subset of that or something like that. And so I think open strings and T-duality is also an interesting question, but we haven't looked at that.
Can you directly do anything thinking about M theory or starting with M dimensions and cosmological reduction? Or do you lack the sort of argument that you've got a half prime expansion?
This is very interesting. The naive picture of 11 dimensions is you have an 11-dimensional R to the 4 term. If you reduce that to the 2A frame or something like that, that's roughly 1 loop R to the 4. And once I say 1 loop R to the 4, then I can't do this T-duality. So I get kind of stuck. However, if you try to be a little bit clever, you might be able to sort of reduce it, a little bit more non-trivially. Maybe not 11 dimensions, maybe F theory type stuff a little bit, and give it some actual dynamics on the torus or something like that. It's not something I've looked at, but I think there might be some possibilities. Vaguely the point of giving it dynamics on the torus is to have some sort of momentum and winding sort of stuff going on.
It's related to A string, right? 11 dimensions.
Oh, 11 dimensions, yeah.
They're closely related to type 2A.
Right.
So the question is, are there any statements about T-duality in type 2A? Okay. We hear all the
this is on tree level.
2B.
This is on tree level. And so at tree level, 2A, 2B is the same. So whatever I said is 2A or 2B, except for a few places where I sprinkled in 2B.
Well, then why can't we go from 11 dimensions to type 2A first? In a circle. And then,
But what I'm saying is the standard R to the 4 in 11 dimensions is 1 loop 2A. And we're not doing 1 loop.
Oh, I see.
Yeah, now this is tree level 2A or tree level 2B. And the tree level 2A does not lift to 11 dimensions. Unless you're a little clever about that. You just got to trace where the Dalton factors are, but I think there's a more sophisticated point of view also, I think. So I think you can do, 11-dimensional superparticle amplitudes and find tree level random loops or something like that. So if you're clever enough, I think you might be able to actually do something in M theory, but we haven't done that.
Okay, thank you very much. So for this very nice talk. So let's thank our speaker again. Stop.